Hi! Today we're going to be looking at what the frequency response of our RC circuit is. So, our RC circuit is like this, and in the last video we calculated its transfer function, which looks like this. Now, what information can we get from this equation? From this equation, we can basically just plug in any number of omega and find out what the response is, what the output relative to the input ends up being. So, obviously, numerically speaking, no problem. We get MATLAB, put the numbers in, and that's it. We get graphs and stuff. But sometimes we don't have that tool available. So I'm going to show you a quick and easy method to more or less see what it does at different frequencies. So we're going to be probing this transfer function at 3 different frequencies. Frequencies that are very low, frequencies that are very high, and at our special frequency that is the pole of our transfer function here. So what we need to do in order to do that first is to calculate the magnitude and the phase of our transfer function as is, without plugging any numbers yet. So we calculate first the magnitude of the transfer function. The magnitude of the transfer function is just the magnitude of this number. So here we have a complex division of 2 complex numbers, and we want to get the magnitude of that. So the magnitude of a quotient is the quotient of the magnitudes, exactly. So I get here the magnitude of my numerator and the magnitude of my denominator. Now the numerator is a real number and the magnitude of a real number is the real number. So that's easy. Sorry. Over. And on the denominator we have a complex number, and we know that the magnitude of a complex number is the square root of the real part squared plus the imaginary part squared. So, this is my magnitude. Yes, that's my magnitude. And my phase, I'm going to calculate here on the right. The phase of my transfer function is the phase of this number. Sorry. Yeah. So here we have again a quotient, and the phase of the quotient is the phase of the numerator minus the phase of the denominator. So we do the phase of h of j omega equals the phase of 1 over RC minus the phase of j omega plus 1 over RC. Now, the phase of a real number is 0. And the phase of an imaginary number is the inverse tangent of the imaginary part over the real part. So in this case, is minus inverse tangent of RC omega, I believe. Yeah. So here we have, I'm going to write it down here so that we have them close to each other. So the phase of my is this number. So what do we do with these two equations now? First, let's see what happens when omega is very, very small. When omega is very, very small, this number goes to 0. Then I get 1 over RC squared, square root of that. So this square root goes away, and then I get 1 over RC over 1 over RC. So I get 1. So omega tends to 0. Then the magnitude of my transfer function tends to 1. Now we can see what happens when omega is very, very, very big. So if this number is very, very big, squared is even bigger, and this number doesn't affect it, and this is basically a very, very, very small number, or a relatively small number, over a very, very, very big number. So my transfer function tends to 0. Because I have a small number over a very, very, very big number, so that's 0. So when omega tends to infinity, then the magnitude of the transfer function tends to 0. And now I want to see what happens when our frequency is 1 over RC, which is my pole of my transfer function. We talked about that last time, and it's interesting to see what happens there. So I'm going to substitute omega by 1 over RC to see what happens. So I would have the magnitude of h of j omega would be equal to 1 over RC over square root of 1 over RC squared, and then I put again 1 over omega or RC because I want omega to be 1 over RC, so plus 1 over RC squared. So that gives me basically 2 times this. And this basically becomes over RC over square root of 2 times square root of 1 over RC squared. And then this square, sorry, that's not correct, squared. And this squared goes away with the root. So I get 1 over RC over square root of 2 times 1 over RC. And then this one goes away with this one. And I get that my magnitude is equal to 1 over square root of 2, which if we represent in dBs, which is 20 times log 10 of 1 over square root of 2 is approximately minus 3 dBs. So at my special frequency, which is the pole of my transfer function, the amplitude of my transfer function is 1 over square root of 2 or minus 3 dBs. Now, basically we can put that here. When omega equals 1 over RC, then the magnitude of my transfer function is approximately minus 3 dBs. And now we can do the same with the phase. We can do the same with the phase. For frequencies that are very, very, very small, I have 0 here. So I have minus inverse tangent of 0, which is 0. So, and the phase of, yeah, that makes sense, of my transfer function tends to 0. When the frequencies are very, very, very big, I have minus the inverse tangent of a very big number, which gives me minus 90. The phase of my transfer function. Tends to minus 90 degrees. And when omega equals 1 over RC, which is my special frequency, my phase, we can calculate that. Yeah, I have here RC and here 1 over RC. So I have minus inverse tangent of 1, which is minus 45 degrees. The phase of my equals minus 45 degrees. So what does this mean? We can basically plot, we can basically plot this behavior in a plot where I have frequency on the x-axis. So it would look like this, somewhere down here. So I'm going to plot my magnitude. Here I have frequency in the frequency axis, or let's put omega to be more precise. And we have our, I'm going to put it in another color, red. The magnitude of my transfer function will look like this. At my special frequency, 1 over RC, I have minus 3 dBs. So I'm going to put here, that's 0 dBs. And here, I'm going to put minus 3 dBs. So at my special frequency, my amplitude is minus 3 dBs. Below that, my amplitude is 1. Where is that? Aha, here. My amplitude is 1, which is basically the input is equal to the output, so I have 0 dBs. And above that, my frequency, my amplitude starts coming down until at the infinity, it's basically 0. So it will look like this. And go down forever and ever on a straight line. So that is the magnitude of my transfer function. Yeah? So with this graph, I can say, okay, for frequencies below 1 over RC, I have pretty much my input equals my output. And for frequencies above, then the amplitude goes down gradually as the frequency increases. And that is what I can get out of this transfer function. Now, this is why this circuit is called a low-pass filter. So every time we have this circuit and we measure the voltage at the capacitor, we have this response, which is a low-pass circuit, which means that the low frequencies pass unhindered and the high frequencies are gradually attenuated until at infinity, at frequency equals infinity, the amplitude of the output is equal to 0. And the phase, I'm going to plot in green, the phase we have, let's say at this frequency minus 90 degrees, 0, minus, exactly. So I have, let's say, minus 45 degrees here and minus 90 degrees here. So we know that at our special frequency, our phase is 45 degrees. Below that is 0, and above that it tends to minus 90 degrees. So my response, my phase, will look like this. Actually, not that much, like this. More like this. So that would be the phase of my output relative to the input. So this is the behavior of my circuit, and just for the record, our special frequency omega equals 1 over RC is therefore called the cutoff frequency. And it's often represented as omega C or FC when converted into hertz. So this is useful because sometimes, for instance, one very useful application of this circuit is an anti-aliasing filter in audio applications, because we're gonna, if we want to record a signal and save it in the computer, we need to sample it. And to sample it, we need to have a sampling frequency. And when we have a sampling frequency, we have to absolutely make sure that there are no frequencies above half of the sampling frequency. So to make sure of that, we apply a low-pass filter with a cutoff frequency of half the sampling frequency. And then we basically eliminate all frequencies that are above that, and we can go and sample our my signal without risk of aliasing distortion. So, yeah, with the help of my transfer function, I can basically, just by plotting 3 points, I can see what type of behavior my circuit has. So in this case, we have a low-pass circuit. In the following videos, we're going to be talking about a very similar circuit like this, but instead of having the output at the capacitor, we're going to measure the output at the resistor, and we're going to see what differences we see. Thanks for watching.